The next kind of parallelism we want to consider is function parallelism. Its name comes from the fact that we can think of a whole loop as a function body and can execute the function bodies in parallel. The first step in doing this is to identify dependencies in a loop body. And find which of the loop bodies are independent, we can split or distribute the loops to different tasks that can be done in parallel. Let's consider this loop that has 4 statements in it. The first statement takes b sub I plus 1, multiplies it by a times I minus 1, and sets a sub I equal to that. The next one multiplies b sub I by a coefficient. The third one takes half of c sub I plus a sub I and assigns it to c sub I. And the third one takes d sub I minus 1 times d sub I and assigns it to d sub I. So let's consider what are the loop independent dependencies in this code sequence. To do that, we look for operands complete with subscript that appear in more than one statement. And there's only one of them. A sub I is used here on the right-hand side and there on the left-hand side. So that gives us a true dependence between S1 and S3, with S1 having to compute a value before S3 uses it. There are quite a few more loop-carried dependencies though. All we have to do here is to look for an array that's used on both sides of the equal sign, doing arithmetic on the subscript on the right-hand side. Well, here's one, here's another one, and there's a third one. So let's list them. We've got a true dependence between the ith iteration of S1 and the I plus first iteration because it uses the a sub I minus 1. We've got an anti-dependence between S2, the ith plus first iteration, and the ith iteration of S1 because we have to make sure that b sub I is not overwritten before it's used right there. And we have a true dependence between the ith iteration and the I plus first iteration of S4 because the ith iteration uses the I minus first element of the array. Now one thing we should notice about this is that S4 has no dependencies with other statements. So S4 can be executed totally independently from the other 3 statements. That suggests that we distribute the loops as follows. We have one loop that does statements S1 through S3 and another loop that does statement S4. We can do further transformations as well, and those are described in the text. For one thing, we can see that all S2s can execute after all S1s without violating any dependencies. Let's take a look at a couple of characteristics of function parallelism. The first thing we note is that you're not going to get a lot of parallelism this way. You can't make use of 1,000 processors by having each one execute a different function. In this case, you only have 2 processors that can get into the action, one executing S1 through S3 and another one executing S4, at least before we do the further transformations that I mentioned a little while ago. The second is that the loops are vastly different in length. So it's going to be difficult to balance the load. You're not going to know that one loop is going to finish before another loop, for example. So you could start a third loop on the same processor that did the shorter of the 2 loops. Nonetheless, we can use function parallelism along with data parallelism when we can't get enough parallelism just by parallelizing the data accesses.